Assalamu alaikum students. I hope you're all safe and sound. Welcome to the 7th lecture on analog and digital electronic circuits, in which we will study small signal analysis of common base and common collector amplifiers. So just like we analyzed common emitter amplifier, um, I will discuss the AC and DC equivalent circuits and find the small signal parameters for both common base and common collector amplifiers. So this is the circuit for a common base amplifier, uh, in which R1, R2, RC, and RE, they form the voltage divider biasing network. RL is the load resistance. Vsig is the signal to be amplified. Rsig models the internal resistance of Vsig. Cin is the input coupling capacitor, and Cout is the output AC coupling capacitor. And CB is another coupling capacitor which actually brings this base terminal to AC ground, as we will see later on. Because in the, like I discussed previously in the last lecture, these capacitances CB, in, and Cout, they will be considered as short-circuited in the mid-band frequency range. So when we short-circuit CB, then this base terminal will be directly connected to ground for the AC equivalent circuit, as I will show later on. So again, I will assume that Vsig is so small that it satisfies the small signal approximation, and it will be called a small source signal. And under this approximation, BJT will be replaced with its linear small signal model, and the overall circuit of the amplifier will become linear, which is why we will perform the AC and DC analyses separately, and then using the principle of superposition, we can combine the results of these two analyses later on to get the overall result. So this is the DC equivalent circuit of common base amplifier. It is obtained by by open circuiting the capacitors and killing the AC sources. So open circuiting all these capacitors disconnects load and the source, and we are left with this voltage divider biasing network, in which the output current and the output voltage, they are given by these usual expressions which we have seen before. And this is the AC equivalent circuit of the common base amplifier. Because we will consider the analysis of the amplifier in the mid-band frequency range, I have ignored all the parasitic internal capacitances, and I have short-circuited all the coupling capacitors. And I have replaced the transistor BJT with its small signal T model. So this is the collector terminal. This here is the base terminal, which is now directly connected to ground because CB has been short-circuited too. So CB here has been considered as short-circuited. So base terminal is directly connected to ground. DC sources are killed, so this node is directly connected to ground because VCC is short-circuited. So this nodal surface is directly connected to ground, which brings RC connected between collector and ground, and it brings R1 in parallel with R2 because R1 is connected to base on one side and to this node, which is ground on the other side. So R1 becomes parallel to R2. But since base is directly grounded, so that parallel combination R1 in parallel with R2 is actually shorted out of the circuit. So I do not show that parallel combination because it is effectively out of the circuit. So R1 in parallel with R2 is actually a resistor in parallel to this short circuit. But because of this short circuit, it is ineffective, so we ignore it. So this is the collector terminal. We have RC connected to the collector on one side and ground to the other. So RL is connected to collector on one side and ground to the other. Base is directly short-circuited. This is the small signal resistance in the emitter branch. this is the emitter resistance RE because this is the emitter terminal, and this is the source which is connected to the emitter terminal. So this is the augmented. This portion here is the augmented small signal T model of the device. I've chosen to use T model because it makes the analysis rather convenient. So Ri here labeled here is actually the input resistance of the amplifier. This is the input port. The port which is made up of this emitter terminal and ground is the input port. So resistance seen looking into the input port is the input resistance of the amplifier. This here is the output port. Before the load, uh, this this node, the collector node and the ground makes the output port. So resistance seen looking into the output port is called R naught, and Vi is the voltage at the input port of the amplifier. So it is called the small signal input voltage of the amplifier. So again, you can see that this model is not, if we consider R naught, then this model is not unilateral because there is a path from the output to the input through this R naught. So any change in the output is coupled with the input. So output can affect input, and this is not a unilateral. Considering R naught, this is not a unilateral model of the amplifier, which means that as discussed before, if the amplifier is not unilateral, then the input resistance should be computed without any constraint of open circuiting the output. So we will compute Ri without open circuiting the output. In other words, we will compute Ri considering RL. So Ri here, again, Ri can be just like we did in the case of common emitter amplifier. Ri can be thought of as the resistance, which is Re in parallel with the resistance seen looking into this side of the amplifier. So you can think of this emitter node here after Re, this emitter node and this ground node as another port. And the resistance seen looking into that port is obviously in parallel with Re. And that parallel combination with Re gives us Ri. So this resistance here, which is the resistance seen looking into the port made up of this node and ground, is actually the resistance seen looking into the emitter terminal. And this resistance is found by finding the voltage across the port, which is Vi, and current into the port. Since current out of this port is labeled as IE, we can think of the current into the port as minus IE. So minus IE is the small current flowing into the emitter port, into the emitter terminal, and Vi is the voltage across this port. So Vi over minus IE is the impedance seen looking into this port, which is in parallel with Re to give Ri. So I have written this Ri as Re in parallel with Vi over minus IE. Notice that Vi is actually minus VBE because Vi is the voltage of emitter with respect to ground. And base is grounded. So Vi is actually the voltage of emitter with respect to base, whereas VBE is the voltage of base with respect to emitter. So it is minus Vi. So Vi is minus VBE, or VBE is minus Vi, one and the same thing. So Vi over minus IE is actually minus VBE over minus IE. And IE is equal to the current flowing through R naught, which is labeled as IR naught, plus the current flowing through this small signal resistance, small Re, which is given by VBE over Re in this direction, towards the left. So this is what I've written. IE is IR naught plus VBE over Re, and IR naught is the current flowing through R naught, which is given by this expression. So this can be obtained by, because IR naught is the current flowing through R naught, so voltage across R naught is VCE, because this is the collector terminal, this is the emitter terminal. So this voltage here, voltage of this node with respect to this node is VCE, which is VC minus VE. And VC, the voltage at this node is actually this parallel combination, RC in parallel with RL times minus IC, because IC flows this way, minus IC will flow into this equivalent resistance of RC in parallel with RL. So VC is minus IC times RC in parallel with R0, RC in parallel with RL divided by R0, and VI, like I said, is minus VBE. So minus VI is plus VBE. So I can replace minus VI with plus VBE over R0. So minus VI over R0 is plus VBE over R0. IC is again the sum of two currents. So IC is actually equal to GMVBE plus IR0. So IC is GMVBE plus IR0. And I can take the terms corresponding to IR0 onto the left-hand side, solve, and this is what I get. So I get IR0 in terms of VBE. So when I put this equation back here, I will get this expression. So here, what I've done is I have replaced IR0 with this expression. And after taking LCM and taking this VBE out common, I get this factor. So VBE over IE is actually the inverse of this factor, in which I have replaced small re with its definition alpha over GM. So this re is alpha over GM. GM re is alpha. So I replaced re and the product with alpha and alpha over GM. So re is alpha over GM. This re is alpha over GM. GM re is alpha. And then I have multiplied the numerator and denominator with GM to get this expression. So this factor in parallel with RE gives me the input resistance of the common base amplifier. Again, like we did with in case of common emitter amplifier, we will, after deriving the exact expression, we can use some very reasonable and well-founded assumptions to get commonly encountered approximate results. So in this exact expression, if I assume alpha to be 1, which is not a bad approximation, and assume that R0, small R0 is much, much greater than this parallel combination, which is typically the case, then since alpha is 1, this term is 0, alpha is gone, alpha is 1 here. So the numerator is R0 because R0 is much, much greater than this factor. So numerator can be approximated with R0. Denominator becomes 1 plus GM R0. Since R0 is large, GM R0 is much greater than 1. So you can assume the denominator to be approximately GM R0. R0 gets cancelled and you're left with 1 over GM. And since alpha is taken to be 1, 1 over GM is small re, according to this definition. So this is the commonly encountered expression for the input resistance of the common base amplifier, which can even be further simplified because typically small re is of the order of tens of ohms and capital R is of the order of kilo ohms. So small re is much, much smaller than capital Re. So this parallel combination is approximately equal to small re. So sometimes you'll find the input resistance of common base amplifier to be written as small re. Output resistance of the amplifier is found in a similar way. So if we go back and look at the AC circuit of the amplifier, so output resistance is seen looking into this port. It's found by looking into this port. And again, we know that we know RC, so we can find the resistance looking into this port. Before RC, you can consider this collector and ground terminal making another port, and resistance seen looking into that port is in parallel with RC which gives us R0. So output resistance of the amplifier is obtained or computed by short circuiting the input of the amplifier. So this is the input port of the amplifier. This emitter, terminal, and ground constitutes the input port of the amplifier. So we directly short circuit this emitter to ground, setting VI to 0. Which essentially short circuits RE out of the circuit. So RE is shorted out of the circuit because of this connection of emitter, direct connection of emitter with the ground. So setting VI to 0 means that connecting this emitter directly to ground, which short circuits RE. In addition, I connect a current source here at the collector, so between this terminal and ground, and measure its terminal voltage to find this resistance seen looking into the collector. So the reduced circuit AC equivalent reduced circuit for finding out the resistance seen looking into the collector is given by this diagram here, in which, like I said, the emitter terminal is directly connected to ground, which short circuits RE, so it can be ignored. And a current source is connected at the collector, between collector and ground. And we measure the terminal, its terminal voltage Vs. Now, the ratio of Vs to Is gives us the resistance seen looking into the collector terminal. And then the parallel combination of that resistance with RC gives us R0. Now, this ratio can be found very easily by looking at this circuit. So if we analyze this circuit, then emitter is at ground, base is at ground, which means that VBE is 0 because both ends of RE are the same potential, they are grounded. So VBE is 0, which means that this current source is open circuited. This current is 0 because this current depends upon VBE, so this current is 0. So this source is open circuited, which means that this branch is out of the circuit. We can ignore it. So all we are left with is R0, which is small R0, which is directly connected to the current source. And hence Vs over Is equals small R0, which gives us the output resistance of the common base amplifier as RC in parallel with small R0. Furthermore, we can find the output resistance of common base amplifier by, instead of short circuiting Vi to 0, we can short circuit V sig. So we can short circuit V sig. So short circuiting V sig, the output resistance of the amplifier in that case is denoted by R out. So R out is obtained by short circuiting V sig. So when we short circuit V sig to ground, then this terminal, this end of R sig is connected to ground, which brings R sig in parallel with RE. So emitter is not grounded anymore. Instead, emitter is connected to a resistor whose equivalent resistance is R sig in parallel with RE. So this R sig is actually one, when we short circuit V sig to ground, this R sig is in parallel with RE. And again, I connect a current source here and measure the terminal voltage to find the resistance seen looking into this collector port, into this port. And that resistance in parallel with RC will give us R out. So the reduced AC equivalent circuit to find R out is it's shown by this diagram here. So in this diagram, so like I said, R out is RC in parallel with the resistance seen looking into the collector, excluding RC. So we connect a current source with the collector terminal between collector and ground. And like I said, the emitter is not at ground anymore. Instead, there is a resistor with equivalent resistance R sig in parallel with RE connected between emitter and ground. So we need to find the ratio of the terminal voltage Vs to the current Is to find the resistance seen looking into the collector terminal. And that ratio can be found very easily by analyzing this circuit on the right. So this circuit is actually exactly equivalent to the circuit on the left. It is just a redrawing. This circuit on the right is just a redrawing of the circuit on the left. So I've drawn it in a way which makes it look easier to analyze. So what I've done here is that I have, since this end of the source is connected to ground, so I have shown this source connected to collector and ground separately. So this node is connected to collector, this node is connected to ground. And then I have shown this end of the resistor RE connected to ground separately. So basically this is the same node. So we have R0 connected to collector on one side and to this node, which is this node on the other side. And then to this node, we have this resistance connected, and then we have small RE connected between this node and ground. So this circuit on the right is actually exactly the same as this circuit. It is just drawn in a way which makes it look easier to analyze. So we can write the current in this circuit, Is, as the sum of currents flowing through this branch and this branch. So the current flowing through this branch is GMVBE, and the current flowing through this branch is the voltage across this branch, which is the voltage of collector with respect to ground, which is Vs, divided by the equivalent resistance, which is small r naught plus this parallel combination. So I write IS as GMVBE plus the current through the branch, which is Vs over the equivalent resistance. And then I realize that VBE is actually, so this voltage VBE can be found by using voltage divider rules. So this overall voltage of collector with respect to the ground is divided between R naught and this parallel combination. So the voltage at this node with respect to ground is given by this parallel combination divided by this parallel combination plus R naught times the total voltage Vs. And VBE is negative of this voltage with respect to ground. So this voltage with respect to ground is found by using the voltage division rule, and then voltage VBE is actually the voltage of ground with respect to this node. So VBE is negative of the voltage of this node with respect to ground. So VBE is minus Vs times this fraction, which is obtained from the voltage division rule. So we see that the denominator of these two terms is the same. Vs is common, so we take Vs out common, and then Vs over Is is actually the inverse of this factor, and hence this ratio is given by this expression. And this results in the overall output resistance of the source plus the common base amplifier, which is given by RC in parallel with this factor. So again, we make use of these very reasonable assumptions that R naught, small r naught is typically much greater than RC. So if that is the case, then small r naught is definitely much greater than this parallel combination, because like I said, small RE is pretty small, of the order of tens of ohms, and R sig for typical signal generators is around 50 ohms. So small RE and R sig, they are both much smaller than capital RE, which makes this parallel combination smaller than small RE. So this parallel combination is pretty small. So if R naught is much greater than RC, then it is definitely much greater than this parallel combination. So in the expression for the output resistance of common base amplifier, when R naught is much greater than RC, then capital R naught is approximately given by RC. This parallel combination becomes approximately equal to capital RC. So R naught is approximately equal to capital RC. And in this case, for R out, when small r naught is much greater than this combination, then the numerator is approximately small r naught, and the denominator is less than 1, because like I said, this combination is smaller than small re. So we know that gm times small re is alpha, which is less than 1, but gm times this combination is smaller than gm times small re, because this resistance is smaller than small re. So this factor is less than alpha, and alpha is less than 1. So 1 minus this factor is less than 1. So the numerator is R naught, the denominator is a factor smaller than 1. So the overall factor is even greater than R naught. So since R naught is greater than RC, this factor is even greater than R naught, which is even greater than RC. So hence R out is again given by RC. So this is the commonly found expression for the output resistance of common base amplifier, as well as the output resistance of common base amplifier, including the source resistance. Now, this is the circuit, AC equivalent circuit, for finding the open circuit voltage gain of common base amplifiers. So this is actually the same circuit I showed before, but the only difference is that here I have removed RL, which is equivalent to putting RL to infinity. And I call the voltage at the collector V naught, the open circuit output voltage. So I intend to find V naught over VI. So V naught over VI is the open circuit voltage gain. So in this case, we can see that V naught is given by the current flowing through RC, which is minus IC times RC. So V naught is minus IC times RC. IC is the sum of these two currents, IR naught plus GMVBE. So V naught is minus ICRC and IC is the sum of these two currents. So we've already found IR naught previously in equation 4. And the only difference between that circuit, which we use to derive IR naught in equation 4 and this circuit is that RL is infinity. So if I put RL infinity into the expression for IR naught, which I obtained earlier, then I will get the expression for IR naught corresponding to this circuit. So putting RL to infinity in the actual expression for IR naught, I get the IR naught for this circuit in which RL is infinity. So and as discussed earlier, VBE is equal to minus VI, because VI is the voltage of emitter with respect to ground and VBE is the voltage of ground with respect to emitter. So putting this IR naught into this equation and realizing that minus VBE is equal to VI, taking the LCM and simplifying, we get this expression for the open circuit voltage, output voltage of common base amplifier. So dividing with VI on the left hand side, we get this factor as the open circuit voltage gain of common base amplifier. The overall voltage gain of common base amplifier is obtained by computing the voltage across the load resistor RL. So now let me go back to the actual circuit, the AC equivalent circuit of common base amplifier. So the overall voltage gain is the ratio of the voltage across the load resistor, which is VL, to V sig. So we note that the only difference between this circuit and the circuit I just showed you for the computation of open circuit voltage gain is this. The only difference is the presence of this RL. So in the circuit we just used to find out the open circuit voltage gain, RL was infinity. Here RL is finite. So I can combine this RL with RC, and I will exactly get a circuit which looks, so I will get a circuit by combining RL with RC, which looks exactly like this. So if in the actual AC circuit, which I just showed, if I combine RL with RC, I will get a circuit which looks exactly like this. The only difference will be that instead of RC, I will have a resistance RC in parallel with RL. And instead of V naught, I will call this voltage VL. So, which means that I can directly use this expression obtained for V naught to compute VL. So I compute VL by using this expression for V naught, and in this expression I replace RC with RC in parallel with RL, because when I connect the load resistance, then I can combine the load resistance with RC and convert the two parallel resistances into one, hence obtaining this circuit again. So I've already found the output voltage for this circuit, which is this. So VL now, which is the voltage when this resistance is actually RC in parallel with RL, is given by this expression in which I replace RC with RC in parallel with RL. So the load voltage is again, like I said, is given by this expression by simply replacing RC with RC in parallel with RL. You can derive this expression from the scratch as well. So in fact, I recommend that you derive this expression yourself. So what you can do is, let me go back to the actual AC equivalent circuit. So on exactly the same lines, the way we derive V naught, what you can do is you can combine these two resistances into one and realize that VL is actually minus IC times RC in parallel with RL. And IC is the sum of these two currents, GMVBE and IR naught. And then you use the expression for IR naught, which we derived earlier, and you use the full expression without any constraints of putting RL to infinity. You use the full expression. Use the full expression, you simplify for VL, and you will exactly get the result I just showed you. which I obtained through this shortcut of replacing RC with RC in parallel with RL. So you will exactly get this result. Similarly, in order to find the so once we have this load voltage, I can divide on both sides with VI, and I will get this factor as the overall loaded gain of the common base amplifier multiplied with this factor. So the overall voltage gain VL over Vsig is this factor, which is VL over Vi, times Vi over Vsig. So Vi over Vsig actually takes into account the effect of loading on the input side. So Vsig is divided between Rsig and the resistance seen looking into the input of the amplifier, which is Ri. So Vi is Ri divided by Ri plus Rsig times Vsig. So Vi over Vsig is this factor. So VL over Vi is this factor times Vi over Vsig, which is this factor, gives us the overall voltage gain of the amplifier by this expression. So again, we can make use of these reasonable assumptions that small r0 is much greater than RC and alpha is approximately 1, which gives the input resistance of the amplifier as this and the output resistance of the amplifier as RC. So in this expression for the open circuit voltage gain, if small r0 is much greater than RC, then the denominator is approximately small r0. And since small r0 is large, GM r0 is much greater than 1. So the numerator is approximately GM r0. So r0 gets cancelled and we are left with this expression, GM RC, for the open circuit voltage gain of common base amplifier. On the other hand, for the loaded voltage gain, since small r0 is much greater than RC, it is definitely greater than this combination because this parallel combination is smaller than RC. So the denominator here is again approximated by R0. Because R0 is large, GM R0 is much larger than 1, so the numerator is approximated by GM R0. So R0 gets cancelled out, and we're left with GM. So this factor is approximated by GM. So the loaded voltage gain is given by GM times RC in parallel with RL times. So this is RI. So RI is approximately given by this parallel combination. So RI over RI plus RC. So these are the approximate and more commonly found expressions for the open circuit voltage gain and overall voltage gain of common base amplifier. So this is the circuit to find the AC equivalent circuit to find the short circuit current gain of common base amplifier. So this is the same circuit as before. We have just shorted RL to ground. So RL has been replaced with short circuit, which essentially short circuits RC. So RC has been effectively shorted out as well. So IOS represents the short circuit output current. And we intend to find IOS, the ratio of IOS to ISIG, because ISIG is the input current of the amplifier. So IOS can be seen to be equal to minus IC. So IC is the current that flowed into the collector. So IOS is minus IC, and IC was equal to GMVBE plus IR naught. So IOS is given by minus GMVBE minus IR naught. IR naught has already been found before for the circuit in which RL was non-zero. The only difference between that circuit and this circuit is that RL has been set to 0. So we can use the same expression we derived for R0 in equation 4 by simply putting RL to 0. So IR0, the reduced expression for IR0 is given by VBE over R0. And it can be seen directly from this circuit here as well, because this node is grounded. So this node has a voltage of minus VBE with respect to this node. In other words, this node, which is ground, has a voltage of VBE with respect to this node. And this is the same node as this node. So the voltage across R0 is actually VBE. because this terminal is connected to emitter, and base and collector terminal are both now grounded. So if this voltage, if the voltage of ground with respect to emitter is VBE, then this voltage is VBE because this is the voltage of ground with respect to emitter. So VBE over R naught by definition is IR naught. So we put this expression here, and as before, we observed that minus VBE is equal to VI, and by definition, VI is equal to, so Ri is the impedance seen looking into the input port, which is equal to Vi over I sig. So Vi is I sig times Ri, and we've already found Ri. So in that expression, we can replace RL with 0 and find a reduced expression for Ri. That is, this is the reduced expression for the input resistance of common base amplifier. So Ri when RL is 0 is given by this expression, and so IOS over I seg, which is the short circuit current gain, becomes equal to this factor, as shown here. The overall current gain is obtained by finding the load current. So if we go back to the actual AC equivalent circuit of the common base amplifier, then we observe that IL is a fraction of minus IC. So minus IC flows towards the right and is divided into RC and RL. So the current through RL, which is IL, is a fraction of minus IC, which is given by the current division rule. So IL is minus IC into RC over RC plus RL. And IC is given by the sum of GM VBE and IR naught. So we use these formulations to write IL as minus IC times this factor. IC is GM VBE plus IR naught. We have already found IR naught to be given by this factor. VBE is again minus VI, so VBE is common. We take it outside. Minus VBE equivalently is equal to VI, which is by definition I sig times RI. So we get this expression, or by simplifying this term within the parentheses, we get this expression for IL. And hence dividing by I sig, we get the overall current gain of the common base amplifier, which is given by this long expression, in which we have replaced Ri with its full value, because now RL is connected to the circuit. We don't have to approximate Ri under any particular condition. So we use its full value, full expression. So again, by making use of these reasonable approximations that GM R naught is much, much greater than 1, which typically it is. Small re is much, much smaller than capital Re, which typically it is. And small R naught is much, much greater than this parallel combination of RC and RL, which is a good assumption. Then we notice that since GM R naught is much, much greater than 1, this numerator becomes GM R naught divided by R naught. So this term becomes GM. Similarly, if GM R naught is much, much greater than 1, then GM R naught is definitely much, much greater than alpha, because alpha is less than 1, strictly speaking. So then this denominator becomes GM R naught, and R naught gets cancelled, so we get alpha over GM. So alpha over GM is small re, and we've assumed small re to be much, much smaller than capital Re. So this parallel combination becomes small re. This was GM, so GM times small re is equal to alpha by definition. So the short circuit current gain is approximately given by alpha. So the short circuit current gain of a common base amplifier is almost unity, because alpha is almost equal to 1. Similarly, we can obtain a more convenient approximate expression for the overall current gain of the common base amplifier by using these approximations again. So GM R naught plus 1 is approximately GM R naught. R naught has been assumed much greater than this parallel combination, so this denominator here becomes R naught. So GM R naught over R naught leaves us with GM here. So this factor is GM. Again, this term becomes alpha times R naught because R naught is much greater than this factor. And since R naught is much greater than RC in parallel with RL, GM R naught is much greater than GM times RC in parallel with RL. And GM R naught is then definitely much greater than this term because 1 minus alpha is smaller than 1, which makes this term even smaller than GM RC in parallel with RL. So GM R naught is much greater than this term, and hence this sum of the two terms can be replaced with GM R naught. And then using this assumption that GM R naught is much greater than 1, if this is true, then GM R naught is much greater than alpha because alpha is less than 1. So this denominator, in short, can be replaced with GM R naught. Numerator is alpha R naught, so R naught gets cancelled. Again, we get alpha over GM, which is small RE, which is again assumed to be much smaller than capital RE. So this factor becomes equal to small RE. And this was GM. So GM times small RE is again alpha. So the loaded current gain of the common base amplifier is given by this convenient a good approximate expression. So we notice that there is no negative sign in the short circuit current gain, loaded current gain, or open circuit voltage gain, or in the expression of overall voltage gain of the common base amplifier, which makes this configuration a non-inverting amplifier. So now we move on to the small signal analysis of common collector amplifier, whose circuit is shown in this diagram here, in which, as before, Vsig is the small signal to be amplified. Rsig models the internal resistance of Vsig. C in and C out are the AC coupling capacitors at the input and output. Input is applied to the base. Output is taken from the emitter. RL is the load resistance. And there is no RC. RC is 0 because we want the collector terminal to be at AC ground. So when we find the AC equivalent circuit of this amplifier, then it is found by short circuiting VCC to ground. So this nodal surface is at AC ground. So which makes this collector, which brings this collector to AC ground. So input is measured with respect to AC ground, which is the collector terminal. Output is measured with respect to the AC ground, which is the collector terminal. So both input and output, they are measured with respect, the voltages at the input and output are measured with respect to the collector. So collector is common between the input and output ports, and hence the name common collector amplifier. It is also called emitter follower because, as I will show later on, the output voltage at the emitter follows the input voltage at the base very closely, hence the name emitter follower. Again, I will assume that Vsig is small enough to satisfy small signal approximation, under which the overall circuit becomes linear, and we can carry out the DC and AC analysis separately. So at DC, this is the equivalent circuit of the amplifier, which is obtained by open circuiting the capacitors. So this is a reduced voltage divider biasing network. I call it reduced because RC is 0. So the output collector current and the output collector emitter voltage, they are given by the usual expressions. The only difference is that in this expression for VCE, RC has been set to 0. This is the AC equivalent circuit of common collector amplifier in the mid-band frequency range, where we short circuit the coupling capacitors and ignore the parasitic capacitance. So I have again chosen to replace the BJT with its small signal augmented T model, uh, in which IC, IB, and IE they represent collector, base, and emitter currents. RE, small RE is the resistance in the emitter branch, and small R naught is the resistance between collectors and emitters. So, as I mentioned before, since this AC equivalent circuit is obtained by short circuiting all the DC voltage sources, so this node becomes AC ground. So collector is grounded, and this side of R1 gets connected to ground as well. So that brings R1 in parallel with R2. So I have shown this here in this diagram. So R1 in parallel with R2 has been shown to be this resistance, which is connected between base and ground. And collector is also at ground. So the resistance seen looking into the input of the amplifier is labeled as Ri. So this port is considered as the input port of the amplifier, which constitutes the base terminal and ground. And this input resistance Ri by definition is given by the input voltage across the input port, which is Vi, and the current into the input port, which is I sig. So Ri is given by Vi over I sig. Output resistance seen between this node and ground, which makes up the output port. So the resistance seen looking into the output port is called the output resistance and is denoted by R naught. And like I mentioned, Vi is the small signal input voltage of the amplifier. So we notice that because of the presence of this resistance capital Re, this model of the amplifier or this amplifier circuit is not unilateral because the output is connected to the input through Re. Any change in the output will be propagated back towards the input. For example, if Ve, the voltage at the emitter changes, then for fixed base voltage Vi, VBE will change. Once VBE changes, this current will change. Since this current is beta times IB, then IB will change. And as IB changes for fixed VI, I sig will change. So the change in VE is reflected on the input side, which is why this circuit is not unilateral. And unlike most of the other configurations, for example, strictly speaking, the common base amplifier as well as the common emitter amplifier, they are also not unilateral. But in the case of common base amplifier and fully bypassed common emitter amplifier, if we ignore R naught, then the resulting circuit becomes unilateral. But in this case, irrespective of the fact whether you ignore R naught or not, this circuit is not unilateral because of Re. So we will measure the input resistance without any constraint of open circuiting the load RL. So we will measure Ri considering RL is connected to the output. So like I said, Ri is given by definition. It is the ratio of the input voltage to the input current. And as we did in case of common emitter amplifier, instead of measuring this ratio, we can clearly see that Ri is the parallel combination of this resistance and the resistance seen looking into this port. So if this node and ground can be observed to make another port, then the resistance seen looking into this port, in other words, the resistance seen looking into the base terminal, which is by definition equal to the voltage at the base Vi divided by the current entering the base IB. So this resistance, which is given by the ratio of Vi to IB, it can be clearly seen to be in parallel with R1 in parallel with R2. And this combination together gives us Ri. So Ri is actually this equivalent resistance in parallel with the resistance seen looking into the base. VI over IB. So we can write VI in terms of IB through this expression by noting that VI, the voltage at the base, is equal to VBE plus the voltage at the emitter. Voltage at the emitter is given by this equivalent resistance RE in parallel with RL times IE. And IE is given by the current through small re, which is IB plus beta IB, plus the current through R0, which is IR0. So IB plus beta IB plus IR0 times this equivalent resistance gives us VE. And VBE is given by this first term here. So VBE is the current through RE, small re, which is IB plus beta IB times small re. So this is VBE. And together this gives us VI. So we can find the current flowing through R0 as this. So IR0 by definition is given by this ratio because it is the current flowing through R0. So it is equal to VCE over R0. VC is 0 because collector is connected to ground. VE has just been found to be equal to this expression. So putting this expression in here, we get this form for IR0. So taking the terms connected to IR0 here on the right hand side to the left hand side and solving, we get this expression for IR0, which when put in 29 gives us this ratio VI over IB as this expression. So IB is common in all of these terms. It's common. It's in here. It's also present here, and it is also present in the expression for IB. So I can take IB out common and divide it on the other side. So I'm left with beta plus 1 RE, which is this term, beta plus 1 here, and this factor here. So beta plus 1 minus this factor here, and then this factor RE in parallel with RL. So I can take the LCM and simplify, and this is what I will get for the input resistance, for the resistance seen looking into the input of common, or should I say the resistance seen looking into the base of the common collector amplifier, which can be actually directly observed from this AC circuit here. So if you remember the resistance reflection rule, we can, using that rule, we can find the resistance in the emitter branch and reflect it onto the base side by multiplying with beta plus 1. So resistance in the emitter branch is RE in parallel with RL in parallel with R0. So R0 is actually in parallel with RE and RL because R0 is connected to emitter on one side and ground on the other side. So it is parallel to RE and RL. So this resistance capital RE in parallel with small R0 in parallel with capital RL is in series with small RE. So the resistance of the emitter branch is small RE plus the parallel combination of these three resistors. When it is shifted to the base side, it is multiplied by beta plus 1. So one can directly find this expression. This is the resistance in the emitter branch, multiplied by beta plus 1 is the resistance seen in looking into the base, on the base side. The overall resistance of input resistance of the common collector amplifier is then given by this factor in parallel with R1 in parallel with R2. Again, we can make use of this reasonable assumption that small R0 is much greater than this combination, which means that this parallel resistance becomes almost equal to capital RE in parallel with capital RL. So this is the reduced and more commonly found expression for the input resistance of the common collector amplifier. Then the output resistance of the amplifier is found by solving this circuit. So if you remember, the output resistance of the amplifier is found by short circuiting the input of the amplifier. So this resistance of the amplifier is found by short circuiting this VI to 0, meaning that we short circuit base directly to ground. When we do that, then that short circuit actually essentially short circuits R1 in parallel with R2 out of the circuit. So when we short circuit the input, which is this terminal to ground, then this resistance is shorted out. And we are left with, and since I want to find resistance seen looking into this port, the reduced AC equivalent circuit is given by this diagram, in which base is directly grounded and the resistance, which was R1 in parallel with R2, which was connected to the base and ground, has been shorted out because of this ground connection of the base, and we are left with this simplified AC circuit, in which you can see that the resistance seen looking into the output port is given by the parallel combination of these three resistors. So this voltage controlled current source is grounded on both sides. So there is a short circuit across this current source. So you can think of this node as connected here, because this and this, these two are the same nodes. They're connected to the ground of the circuit. So this short circuit short circuits this current source, so you can ignore it. So we have a short circuit here, which means that if you look closely, then the small RE, capital RE, and small R node, they're all in parallel, because one of their ends is connected to this node, and the other terminal of each of these resistors, that terminal is connected to ground. So this terminal of R0, this terminal of RE, and this terminal of capital RE, they are all connected to the same node here. And this terminal of small re, this terminal of capital RE, and this terminal of small r0, they're all connected to the same ground terminal or the ground node. So small re, small r0, and capital RE, they're all in parallel. So the resistance between this emitter node and ground is the parallel combination of these three resistors. Apart from short circuiting VI, which gives us the output resistance of the amplifier, we can short circuit Vsig, and in that case R0 is labeled as R out, and that is the output resistance of the amplifier plus the source signal, because it includes R sig. So when we short circuit Vsig instead of short circuiting Vi, then this end of R sig will be connected to ground. So the other end is connected to the base, this end is connected to the ground, so that makes R sig come in parallel with this resistance. So base terminal is not grounded anymore. In fact, it will have a resistance. It will have a resistor whose equivalent resistance will be given by R1 in parallel with R2 in parallel with R sig. So the reduced AC circuit for finding R out is given by this diagram, in which, like I said, base is not grounded anymore. It is connected to this resistance, R sig in parallel with R1 in parallel with R2. And here I have shown R0 to be explicitly connected between emitter and ground, because it is connected between emitter and collector is at AC ground, so I explicitly show it to be in parallel with capital RE. So you can clearly see that the resistance seen looking into this port, which is the resistance between emitter terminal and ground, is equal to this capital RE in parallel with small r0 in parallel with the resistance seen looking into this side of the circuit between emitter and ground. So all we need to do in order to find out R out is to find out R out prime, which is the resistance seen between emitter and ground looking into this side of the circuit. So this resistance is found by exciting this node with a voltage source and measuring its current IS. So the ratio of Vs to IS. So IS is the current drawn by this circuit. So the ratio of Vs to Is actually gives us the resistance seen looking into this port between the emitter terminal. So this is the emitter terminal and the ground terminal. So we can find this ratio Vs over Is by representing Vs in terms of Is. So if you notice, then Vs is given by Is times Re. So Vs is given by a voltage drop across Re plus the voltage drop across this equivalent resistance. So voltage drop across Re is Is Re, and the voltage drop across this resistance is the current through this resistance times this resistance. So the current through this branch is Is plus GMVBE. So Vs is actually ISRE plus Is plus GMVBE times the resistance in that branch. Now VBE can be seen to be equal to minus ISRE, because ISRE gives the voltage of this node with respect to this node, and the voltage of this node with respect to this node is negative of that. So VBE is minus ISRE. So we have Is common. In both terms, we take it out and divide it on the other side. Divide by Is on the other side. So Vs over Is is then given by this factor. And the overall resistance of the source plus amplifier is then given by this factor in parallel with small r0 in parallel with capital R0, which can be expressed into this form. So this form is obtained by realizing that alpha is GM over alpha over GM is small re. So GM small re is alpha. So 1 minus alpha. So this becomes alpha. And 1 minus alpha is 1 over beta plus 1. So we have beta plus 1 here in the denominator. And then we observe that from the resistance reflection rule, small re is r pi over beta plus 1. So we write this factor into this form. Again, we can make use of this reasonable assumptions that alpha is pretty close to 1 and R0 is much, much greater than capital RE. So for R0, if for capital R0, the output resistance of the amplifier, if small R0 is much, much greater than capital RE, then it is definitely much, much greater than small re, because small re is smaller than capital RE. And hence it is definitely much, much greater than small re in parallel with capital RE, which is why R0 is then under this approximation given by small re in parallel with capital RE. Similarly, if we use this approximation in this expression, so when alpha is taken to be 1, then this term becomes 0. And we're left with R0 in parallel with capital RE in parallel with small re, in which if we again assume that small R0 is much, much greater than capital RE, then this factor of small R0 in parallel with capital RE in parallel with small re becomes equal to small re in parallel with capital RE. So this is the commonly found and commonly encountered expression for the output resistance of common collector amplifier. We can further simplify it by assuming small re to be much, much smaller than capital RE, which is actually a very good assumption, because small re is of the order of tens of ohms, like I said before, and capital RE is of the order of kilo ohms. So small re in parallel with capital RE is almost equal to small re. So notice that this is the same expression we obtained for the input resistance of common base amplifier. So the input resistance of common base amplifier is actually equal to the output resistance of common common collector amplifier. The reason being that we take the output from emitter. So the resistance seen looking into the emitter is this, and in case of common base amplifier, we apply the input at the emitter. So again, the resistance seen looking into the emitter is given by this factor. So the input resistance of common base amplifier is equal to the output resistance of common collector amplifier. This is the AC equivalent circuit for computing the open circuit voltage gain of common collector amplifier. So this is the same AC equivalent circuit as we saw before, but I have removed RL and I've labeled the output voltage as open circuit output voltage as V0. So we can see that V0 is equal to the drop across RE, which is given by the current through RE times RE. capital RE. So current through capital RE is small IE. So V naught is given by small IE times capital RE. And we see that small IE is the sum of the current through small RE. So it is the sum of current through small RE and the current through R naught. So the current through small RE is IB plus beta IB. So small IE is IB plus beta IB plus IR naught, as shown here. Where we've already computed IR naught back in equation 31. And the only difference in the circuit we used to compute IR naught in 31 and this circuit is that RL is infinity. So in this circuit, I put RL equal to infinity. So in the actual circuit, if I put RL is equal to infinity, I get this circuit. So I don't have to derive IR naught again. Like before, I can use the actual expression for IR naught and simply replace RL in that expression with infinity. So the resulting reduced expression for IR naught given by this term, this factor here, is the current, represents the current through R naught for this circuit. So I put this IR naught into this expression and take IB out common because IB is present here, and in the expression for IR naught as well. So I take IB out common. I'm left with beta plus 1 minus this factor. I simplify the terms within the parentheses by taking the LCM, and I get this factor here. So this is the expression for open circuit output voltage of common collector amplifier. On the other hand, we see that the input voltage VI is given by the sum of the output voltage and VBE. So VI is the voltage at the emitter, which is equal to the voltage across, sorry, VI is the voltage at the base. So it is equal to the voltage across base and emitter junction and the voltage of emitter with respect to ground. So VBE is again IB plus beta IB times small RE. So VBE is given by this term, and V naught has been computed here in this equation. So I plug this expression into this equation. And again, I see that IB is common. So I take IB, I can take IB out common, and I'll be left with this factor plus this factor. So I can divide V naught in 42 with VI in 43 to get the open circuit voltage gain of common collector amplifier. Since IB is common in both equations, it gets cancelled out, and this is what I'm left with. In which, again, I noticed that I can cancel beta plus 1 in the numerator as well as the denominator because beta plus 1 is common in all of the terms. So beta plus 1 has been cancelled out, and observing that this fraction times RE, capital RE, is actually the parallel combination of small R naught and capital RE. Similarly, this capital RE times this fraction is this parallel combination. So I get this fraction as the open circuit voltage gain of common collector amplifier. Furthermore, we can find the overall voltage gain, which is defined as. So if I go back to the actual AC circuit of common collector amplifier, so the overall gain of the common collector amplifier, including the load resistor, is given by the ratio of voltage VL, which is the voltage across resistor RL, to V sig, which is the signal voltage, source signal to be amplified. So VL over V sig represents the overall voltage gain or loaded voltage gain of the amplifier. And again, following the philosophy of the shortcut method I used to find VL in the case of common base amplifiers, I can directly find VL from the expression of V naught I just computed, because if I combine RL with RE and replace the two with a single equivalent resistance given by RE in parallel with RL, then this circuit reduces to this circuit that we just used to compute V naught, this circuit. So if in the actual circuit I combine RE and RL, then I'll exactly get this circuit back. The only difference will be that instead of RE, this resistor will have resistance equal to RE in parallel with RL. And I will designate this voltage instead of by V0, I'll designate this voltage with VL. So, like I said, I can again use this expression for V0 to find VL. The only difference is that I will have to replace capital RE with capital RE in parallel with capital RL. So replacing capital RE in this equation with capital RE in parallel with capital RL, I will get the voltage across the load resistance. So again, I recommend that you go through the derivation from the scratch. You can derive this expression by following this method. So looking at the actual circuit where we have RL as well. So RL in parallel with RE can be converted into single resistor, and the load voltage is then given by IE times RE in parallel with RL. So we'll have RE in parallel with RL here, RE in parallel with RL. So instead of using this reduced expression for IR naught, use the full expression for IR naught, because you don't have to put this constraint anymore, because now you've connected the resistance back, the load resistors back into the circuit. So use the full expression for IR naught derived in 31, and you will get an expression which looks like this, but will have RE in parallel with RL instead of RE. So you will get exactly this expression. Furthermore, we can, because VI depends on V0, so we can directly write VI as the sum of VBE plus VL. So now when I connect the load resistor back, I call the output voltage V0 as VL. So VI is the sum of, so let me go back. So VI is the sum of this voltage plus VL. So this voltage is as before given by IB plus beta IB times small RE. So IB plus beta IB times small RE. This is the voltage across small RE. And the voltage across the load, which is now RE in parallel with RL, is given by this equation. So VI is VL plus VBE. So again, we see that IB is common between this term and this term. So I take the ratio of VL to VI to find the overall voltage gain of the amplifier, which is given by VL over V6. So VL over V6 is VL over VI. So I divide VL with VI times VI over V6. So as before, VI over V6 is RI over RI plus R6. So this is the term that takes into account the effect of loading on the input side. So VL over VI is this divided by this. So IB gets cancelled out because it is common in all the terms. And beta plus 1 can also be cancelled because it is common in both of the terms in the denominator. So it can be cancelled with the 1 in the numerator. And this fraction here multiplied by RE in parallel with RL is actually the parallel combination of R0, RE, and RL. And so is this fraction times this factor. So eventually we get this this factor as the overall loaded voltage gain of common collector amplifier. As before, I can make use of this very reasonable assumption that small R0 is typically much larger than capital RE. If that is the case, then this parallel combination becomes equal to capital RE. This becomes equal to capital RE, and the open circuit voltage gain of common collector amplifiers reduces to this expression. Similarly, I can make use of this assumption for finding out the approximate expression for AV. So if R0, small R0 is much greater than capital RE, then it is definitely much greater than capital RE in parallel with capital RL, because this parallel combination is smaller than RE. So this factor becomes equal to capital RE in parallel with capital RL, because R0 is much greater than this parallel combination. So this parallel combination becomes capital R in parallel with capital RL. So the loaded gain reduces to this approximate expression, uh, in which R naught has been ignored because it is much larger than capital R. So these are the more commonly encountered expressions for the open circuit as well as the overall voltage gain of a common collector amplifier. So next we find the short circuit current gain of common collector amplifier, and this is the AC equivalent circuit. To do that, in which RL has been short circuited to ground. So this short circuit actually short circuits RE, capital RE, out of the circuit as well. So capital RE is shorted out of the circuit and then can be ignored. So IOS represents the short circuit current, output short circuit current, which can be seen to be equal to small IE because this RE has been shorted to ground. So all of this IE will flow through this short circuit. And I intend to find the ratio of IOS to ISIG because ISIG is the input current of the amplifier. So like I said, IOS is equal to IE, and IE in turn is equal to the current through small RE plus the current through R naught. But if you notice, then this current IR naught, which flows through R naught, is actually zero because R naught is in parallel with the RE because R naught is connected to the emitter on one side and ground on the other side. So R naught is also in parallel to capital RE, and hence is also shorted out because of this short circuit. So there will be no current flowing through flowing through R naught. So IE will be given by the current through small RE, which is IB plus beta IB. So IE is IB plus beta IB, and we can actually mathematically verify that in addition to this qualitative argument, we can mathematically justify that IR naught is zero. So if we go back to the expression for IR naught, so if I put RL to zero here, because I have short circuited RL to ground. So if I put RL zero here, then mathematically you can see that IR naught is zero. So the emitter current is given by IB plus, so emitter current is given by IB plus beta IB, or beta plus 1 times IB. Now we can relate IB to the input current ISIG, because ISIG, the input current to the amplifier, is divided between this resistor and IB. So ISIG is actually the current through this resistor and IB. So or in other words, IB can be found by using the current division rule on ISIG. So the resistance seen looking into the base terminal is, as we computed before, is VI over IB. So VI over IB is the resistance seen looking into this base terminal. So ISIG is divided between this resistor, R1 in parallel with R2, and the resistance seen looking into base, which is given by VI over IB. So the current through this resistance looking into the base, which is IB, is given by the current division of ISIG. So small IB is R1 in parallel with R2 over R1 in parallel with R2 plus the resistance seen looking into the base, which is VI over IB times ISIG. So this factor comes from the current division of ISIG between this resistance and this resistance. We have already found the expression for VI over IB in 32. So VI over IB, which is the resistance seen looking into the base, is given by this expression. And we can use this expression by replacing RL with zero, because now the circuit that we are analyzing has an output which is short circuited to ground. So RL is zero. So putting RL to zero in the actual expression for VI over IB, we get the reduced expression for VI over IB, which is given by this term here, beta plus 1 RE, small RE. So IB, so we relate IOS to IB and then IB to ISIG, which gives us a way to relate IOS to ISIG. So IOS over ISIG is IOS over IB, which is beta plus 1, times IB over ISIG, which is this factor here. So the product of this term and beta plus 1 gives us the short circuit current gain of common collector amplifier. So this last equality is obtained by multiplying this factor with small RE in the numerator and denominator. So when I multiply small RE, so when I multiply the numerator with small RE, then R1 in parallel with R2 times beta plus 1 small RE divided by this denominator becomes equal to this parallel combination. And then this small r in the denominator can be written separately. So this is the short circuit current gain, the expression for the short circuit current gain of common collector amplifier. We can find the overall current gain of the common collector amplifier when the load resistor is connected to the output of the common collector amplifier by observing that. So if I go back to the actual AC circuit, in which we have the load resistor connected, so we see that now the current flowing. So the overall current gain is when the load resistor is connected at the output is given by the ratio of IL to the input current I6. So IL can be seen to be given by a fraction of small IE. So small IE divides between capital RE and capital RL. So IL is given by RE over RE plus RL times small IE. And small IE in turn is given by the current through this branch, which is IB plus beta IB plus IR naught. And we've already computed IR naught. So using these formulations, we can find the current flowing through RL, which we denote by IL. And we can find the expression like this. So IL is small IE times RE over RE plus RL. This is the factor from the current division of IE. And IE, like I said, is given by the current through small RE, which is IB plus beta IB, plus the current through R naught. And then we use the expression for the current through R naught, which we derived earlier, which is equal to this expression. And then simplify the terms within the parentheses, and we get this expression for the load current in terms of the base current. So the overall current gain of the common collector amplifier is then given by IL over I6, which is IL over IB times IB over I6. So IL over IB is this factor. So this factor is this. The first two terms represents IL over IB times IB over I6. So we've already found IB over I6 here. So IB over I6 is given by this factor, in which this ratio VI over IB must be used in its entirety, meaning that we should use the full expression for VI over IB without any constraint of putting RL to 0, because now we have connected RL back into the circuit. So we should use the full expression for VI over IB. So IB over I6 is given by this term, in which VI over IB is replaced by its full expression given in 32, which is equal to this term. So this factor represents the ratio IB over I6. So together these three terms, the product of these three terms gives us an expression for the overall loaded current gain of common collector amplifier. As before, we can make use of these reasonable assumptions that small r naught is much greater than this parallel combination. So if small r naught is much greater than this parallel combination, then the denominator here. So let me go back to the expression for short circuit current gain. So the expression for short circuit current gain has this factor, and this factor can be approximated by assuming that R1 in parallel with R2 is much greater than this term, beta plus 1 times this resistance. So if R1 in parallel with R2 is much greater than this resistance, then it is definitely much greater than beta plus 1 times small re, because small re is less than this resistance. So R1 in parallel with R2 is much greater than this factor, beta plus 1 times small re. So the numerator can be approximated by beta plus 1 times small re. Re gets cancelled with the re in denominator, and we get the short circuit current gain as beta plus 1. On the other hand, if we make use of this assumption, then R naught being much greater than this parallel combination means that I can approximate this denominator with R naught, which cancels with R naught in the numerator. So the first term reduces to beta plus 1. The second term is left alone. It comes as it is. And the third term, so I've made the assumption that R1 in parallel with R2 is much greater than this term. So when R1 in parallel with R2 is much greater than this term, then the denominator can be approximated with R1 in parallel with R2. So which then will get cancelled with the term R1 in parallel with R2 in the numerator. So this third factor will become 1. So the reduced overall current gain of the common collector amplifier will be given by this expression. So these are the more commonly found expressions for the short circuit current gain and the overall current gain of a common collector amplifier. And again, we notice that in the expressions for the short circuit current gain, overall current gain, open circuit voltage gain, and overall voltage gain for the common collector amplifier, there is no negative sign, which is indicative of the non-inverting nature of the common collector amplifier, just like the common base amplifier. And furthermore, we observe that the open circuit voltage gain, we well approximated open circuit voltage gain, which is given by this expression, is almost 1, because small re is very small compared to capital RE. So the denominator can be replaced, approximated with capital RE, which will then get cancelled with the numerator. So the open circuit voltage gain of common collector amplifier is very close to unity. It's almost unity, which means that the output AC voltage at the emitter will very closely follow the input AC voltage at the base, which gives this configuration its other name, that is the emitter follower. So with this, we reach the end of this lecture. I hope that you have understood all of the expressions that I have given in this lecture. I highly recommend that you derive all of these expressions for not just the common collector and common base amplifier, but for the common emitter amplifier that we discussed in the last lecture. You should derive all these expressions yourself in order to have an even better understanding of the working of these three amplifier configurations. So thank you very much for your time, and I will see you in the next class. Take care.